Hello everybody, this is the Epic Flight Academy and my name is Mike Thompson. Now our topic today is going to be the magnetic compass, or sometimes it's called the wet compass. Now remember, when we go through these videos, you can't just watch these videos to be successful. To be successful is a three-part process. These videos are number one, but number two, they parallel Epic's online course. And third and finally, be sure to review this content with your flight instructor. So back to that magnetic compass. Why is it called a wet compass? Well, let's start by taking a look at this cutaway. This is a cutaway of a magnetic compass. Now notice how it's constructed. The compass card is what we call a horizontal card, and it's sitting on a pivot point. If that card were allowed to just pivot on this pivot point, hey, we go into a 30-degree bank, it might fall off. Well, what we do is we fill this compass with a clear fluid, much like kerosene, and it dampens the movement of that card as it sits on this pivot point. So if you take a careful look at that cutaway, across the back, you're going to see a rubber diaphragm, and then across the front, of course, you're going to see a clear glass so pilots can see the card. At the top, you're going to see a filler point where a mechanic could drain or refill the fluid inside the compass, and you're also going to see what we call compensating magnets. Now, those compensating magnets are for an airframe mechanic to help determine the compass's deviation. What's deviation? We're going to get to that in just a minute. Now, the final thing I want you to see in this big cutaway is, yes, that card is sitting on a pivot point, and underneath of that card are two magnets. Those magnets will always align themselves with the flux lines of the Earth's magnetic field. Here's a picture of the Earth and its magnetic field. Now, this is exaggerated. These flux lines are exaggerated, but imagine that those magnets inside that compass are always in alignment with the flux lines of this field. Now, if you take a look at this exaggerated picture, as we get closer to the North or South poles, that compass card is going to want to tilt and dip to follow those flux lines. Now, the way that we avoid that with the magnetic compass is, if you go back to this big cross-sectional picture, there are counterweights down below this compass card to help that card stay level at more northern or southern latitudes. Now, if we get close enough to either the North or South Pole, that tipping tendency is going to be so great that the magnetic compass becomes essentially useless. Now, that's not true until we get within probably 300, maybe 200 miles of the pole. And most of us are not flying that close to the North or South Pole. So this instrument is very effective across most of the planet. The beauty of the magnetic compass is it is not powered by anything. Remember, we've looked at previous instrument systems where we needed an air pump to spin a gyro, or maybe we needed electricity to spin a gyro, or we have electrical systems or other types of instrument and mechanical systems. Well, the magnetic compass needs none of that. It just sits there doing its job because those magnets align with the Earth's flux lines. Now, that's the great thing about it. The disadvantage is this compass comes with some errors that we have to deal with. So before we get into those errors, let's look at the face of this compass card. Now, I want you to take a look at the face of this card. Notice right in front of us is a big N with the line through it. That line is called a lubber line. L-U-B-B-E-R, lubber line. That's an old nautical term. And the lubber line is showing me the heading on this card. So in our example, notice the big lubber, the thin lubber line is going through that large capital letter N. Looking at this compass card, that means I would be traveling to the north. Now, if I'm traveling north, think about this for a second. Off to my right would be which cardinal direction? If you said east, you're correct. And off to my left would be which cardinal direction? If you said west, you're correct. Now take another look at this card. If you look closely at this card, off to the right, the numbers indicate northwest and eventually west. And off to the left of the card, the numbers indicate northeast and eventually east. Now that's kind of backwards. Well, it's backwards on the card, but it's not really backwards. Take a look at this next picture. Here we have a horizontal compass card showing us traveling approximately 030 degrees or northeast. We are looking at the back side of a horizontal compass card. So, in fact, I am traveling 030. The card's telling me I'm going 030, but I'm looking at the southwest side of this horizontal compass card if I were to look at it with a bird's eye view. So that's the first consideration about magnetic compasses. It's not really an error, it's just something we have to be conscious of because of the way that it was built. Now, let's take a look at the common magnetic compass errors. We generally break this down into 4 types of errors. The first 2 errors, variation and deviation. These are not necessarily an error of the compass itself, but these are errors caused because of the way we want to use the compass and where we locate the compass. What do we mean by that? Well, let's start with variation. Variation is the difference between the true and the magnetic poles. Have a look at this diagram. The true North Pole is an imaginary spot where we have drawn lines of longitude that connect the North and South Pole of the planet. These imaginary lines of longitude connect at true North and true South. Well, in addition to that, we have magnetic north and magnetic south. Now, these are not man-made. These poles are a result of the fact that the Earth has an iron core. Iron is a ferrous material, which means it's very magnetic, and this causes our planet to have a magnetic field. These magnetic flux lines run into the North Pole and out of the South Pole, making this magnetic field. That magnetic North Pole is not at the same location as the true North Pole. Now, if I were to take a line from the true North Pole and draw it straight south through the magnetic North Pole, that line we would call the agonic line. And you can see that agonic line right here in this diagram. What that means is if I was in my airplane flying to magnetic north on the agonic line, I would need 0 correction to go straight north to true north. Now, if I'm not on the agonic line. Let's say I'm east of the agonic line. Look back at our diagram. Maybe we're over here in the Carolinas or Virginia. And if I head to that magnetic North Pole, I'm not going to go straight to the true North Pole. And so I have to put in some westerly variation. If you're studying at Epic Flight Academy and you're flying around beautiful New Smyrna Beach or Daytona Beach, you can look on your sectional chart and you'll see just offshore a dashed purple line that says 7W. 7 degrees west. What it means is we are east of the agonic line and we need 7 degrees of west variation correction. By the same token, if you look back at our chart and we were flying out west, maybe in Colorado or somewhere, we would need an easterly variation to correct for that difference between magnetic and true north. So that's variation. Now, what's the second one? Deviation. Let's take a look at that. Think about the root word of deviation. It means deviate. It means deviant. It means naughty, naughty, naughty. This naughty compass is not telling us exactly what it should tell us. Why is that? What makes a compass deviate? Deviation is caused by things in your aircraft that will affect a magnetic field or create a magnetic field. And that's going to make those little magnets in that compass, we looked at those earlier, it's going to make those little magnets deviate. Well, like what? Well, you have an alternator in your aircraft. That's a pretty powerful magnet. That's going to cause some deviation. Current flowing through electrical conductors creates small magnetic fields. That may cause some deviation. If you were to take an iPad and just set it up on the up there on the window next to the magnetic compass, you'd see that magnetic compass start to swing. That causes deviation. So the way we correct for this is a mechanic will take this aircraft and park it out on the aircraft on a known magnetic heading, turn everything on in the airplane, engine, radios, etc., and record how much deviation this compass has on that heading. Your airframe mechanic will then write that deviation down on this little card right here. It's called a deviation compass card. And up at the top, it shows the actual compass heading, and then right below it, it shows the deviation of that compass. And notice in our example, it shows it radios on and radios off. Okay, so that's deviation, and that's a compass deviation card. Now, those first two errors, variation and deviation, yes, those are compass errors, but is that really the fault of the magnetic compass? Well, remember, variation was the difference between true and magnetic north. That's not really the compass's fault. Deviation, naughty, naughty compass. Well, that's because I turned on radios and alternators, and that's not really the fault of the compass either. The next two errors are magnetic dip errors and acceleration errors. Now, those really are more a fault of the compass and compass design. Let's take a look at acceleration error. Here is a graphic from the PHAC. The PHAC, the Pilot's Handbook of Aeronautical Knowledge. Okay, this diagram you'll find in the PHAC. This diagram shows us an aircraft accelerating. When the aircraft accelerates, and you can see this depicted by the red dashed lines here in our diagram, the aft end of that compass sort of picks up. And when it does that, the compass swings to a northerly heading. That's an acceleration error. Now, why is it swinging like that? Remember when we first talked about the wet compass or the magnetic compass, and we talked about that card sitting on the pivot, and we talked about the fact that it's got some counterweights to help stabilize that card? The interaction between these magnets and those counterweights cause that card to turn toward the north when we accelerate. Now we're flying along, we pull the throttles back and we decelerate. Notice in our diagram, this is the wavy yellow line here. The forward end of the card lifts up and those magnets and those weights interact and the compass turns toward a southerly heading. Now some of you may have heard this mnemonic, ANDS or hands. A-N-D-S, ANDS. And what it means is accelerate north, decelerate south. When I accelerate the airplane, the aft end of the card lifts, turns north. When I decelerate the airplane, the forward end of the card lifts, turns south. ANDS, ANDS acronym. Well, that brings us to our final error. And these are magnetic dip errors. Now, to understand dip errors, let's go back to that cutaway and remind ourselves, yes, it's a horizontal card sitting on a pivot and there's weights underneath of that pivot. Also, remind yourself, take a look at the flux lines of the Earth's magnetic field. Remember, those magnets want to stay in line with those flux lines, but the weights help to stabilize that card, to keep that card level as we head north and south. Well, what's happening with this turning error? It's a dip error, and it happens when we turn. If we're on a northerly heading and we turn the aircraft to a southerly heading, as we turn towards the south, that card will dip with the weights and the magnets will try to follow those flux lines during the time the aircraft is turning. And the card will turn past the heading we need to get to, heading south. Okay, so we have to lead the rollout. That's what we mean when we say to the south, the compass leads. Now, the opposite happens when we turn towards a northerly heading. When we turn towards a northerly heading, the card lags. And it's the same thing. The airplane is turning north and the card starts to swing. The magnets want to follow the flux line, but the weights below that card are trying to hold it level, and those interact to cause this northerly turning dip error. So that leads us to our final acronym. And that is to undershoot the rollout on a northerly heading and overshoot the rollout on a southerly heading. And the acronym is UNOS, U-N-O-S, undershoot north, overshoot south on the rollout. So those are the 4 magnetic compass errors and a little bit of background on how that compass is constructed and put together, and so why we get those errors, and a little bit of overview on the beauty of the magnetic compass. It doesn't need any power systems. That's the advantage, but it has a few errors to deal with. That's the disadvantage. All we need to do is study the online course now, work with our flight instructor, watch some of these errors in the aircraft in flight, and presto, once we understand the errors, this is a very valuable flight instrument. Well, folks, that is it for the magnetic compass. We will see you next time.